The evening sky over Melbourne Airport was muted, a slate grey stretching toward the horizon. Rain fell in fine, persistent sheets, blurring the edges of taxiways and runway lights into halos. The low hum of distant jet engines mingled with the rhythmic thrum of rain against the tarmac. Inside the air traffic control tower, monitors glowed dimly, tracking the steady descent of aircraft from across the southern skies. Controllers spoke in clipped, precise exchanges, flight numbers, altitudes, headings, voices punctuated by the occasional crackle of interference. Every movement, every transmission, was measured. Silence lingered between messages, heavy with anticipation. High above, the TAA DC-9 cut through the low clouds, wings slicing the humid air. Its approach was routine, yet the atmosphere felt charged, a tension born not of fear but of meticulous timing. Instruments blinked, autopilot adjustments whispered, the crew's eyes scanning, hands ready, minds alert. Outside, the runway glistened under rain-soaked lights, the final target of a descent that demanded focus and precision. Moments stretched. The aircraft shadow danced across the cloud layer, a silhouette approaching the illuminated runway. Each second compressed the space between expectation and consequence. The airport seemed to hold its breath. Even in these first instances, the chain of events that would unfold, small decisions, system nuances, and environmental forces, was already in motion. The story of this flight was not yet tragedy, only the quiet prelude of aviation's exacting demands. By 1996, Trans-Australia Airlines, a legacy carrier operating under the Qantas umbrella, had a long history of domestic service. Its fleet included the McDonnell Douglas DC-9, a workhorse of short to medium-haul routes. The DC-9 had earned a reputation for reliability, simplicity, and efficiency, a twin-engine jet capable of handling Australia's diverse climates and airport conditions. Yet, like all aircraft, it demanded strict adherence to procedures and vigilant crew oversight. Melbourne Airport, the setting for this flight, was a hub of both domestic and international activity. Runway 16, the primary approach for southern arrivals, stretched into the city's outskirts, its lighting system calibrated for low visibility conditions. Pilots relied on a combination of instrument landing systems, ILS, and visual cues, especially during inclement weather, to maintain the correct glide path. On the evening of the incident, persistent rainfall and low cloud ceilings created a challenging environment, compressing decision-making windows for both flight crews and controllers. The crew of the TAA DC-9 was experienced. The captain had accumulated thousands of flight hours, with decades of domestic flying under his belt. The first officer, while younger, had recently completed advanced DC-9 training and demonstrated competence in instrument approaches. Both pilots were trained in standard operating procedures. Yet the sequence of events that evening would test the limits of their experience. Environmental factors compounded operational complexity. Rain-slicked runways reduced friction, cloud cover obscured landmarks, and shifting wind patterns introduced subtle deviations in approach alignment. Each of these elements, individually manageable, formed a cumulative backdrop against which the aircraft systems and the crew's decisions would interact. The DC-9 itself was a product of design choices suited to efficiency and redundancy. Its cockpit instrumentation provided continuous feedback, but also required constant interpretation. Airspeed, altitude, vertical speed, and glide path indicators demanded coordinated attention, particularly during instrument approaches. Even minor deviations, if uncorrected, could escalate into larger errors that could converge within the narrow window of a final approach. This was a world in which the flight operated, a convergence of human expertise, mechanical precision, and environmental unpredictability. Every factor set the stage for the challenges to come, revealing how aviation depends as much on preparation and vigilance as on raw technology. The anatomy of any aviation incident lies in the intersection of multiple angles: the aircraft itself, the human operators, the environment, and the systems that mediate their interaction. In the case of the TAA DC-9, each angle reveals a layer of precision and vulnerability, a delicate balance that demanded absolute attention. Aircraft. The McDonnell Douglas DC-9 was designed for short-haul operations, emphasizing simplicity and reliability. Its twin-engine configuration provided redundancy, while hydraulics and flight controls offered responsive handling. Yet, in adverse weather, its performance envelope required meticulous adherence to speed, altitude, and flap settings during approach. On this evening, the aircraft systems were fully operational. Engines responding, flaps extended as per procedure, autopilot engaged, and instrumentation providing continuous feedback. The challenge was not a failure of machinery, but the orchestration of multiple parameters under dynamic conditions. Crew. The cockpit environment reflected experience tempered by standard operating procedures. The captain, a seasoned pilot, maintained a calm, deliberate approach, monitoring instruments and environmental cues. The first officer, confident but relatively newer to complex approaches under heavy rainfall, provided cross-verification of altitudes, airspeeds, and headings. Training emphasized redundancy, see and confirm practices designed to prevent single-point errors. Yet, human factors, momentary lapses in attention, subtle misreading of instruments, or misjudgment of environmental cues could accumulate. Aviation psychology identifies such chains as error cascades, where minor deviations compound rapidly in critical phases. Environment. Melbourne Airport's southern approach demanded heightened awareness. Rain reduced runway friction and reflected landing lights, while low cloud ceilings concealed peripheral visual references. Wind shifted subtly across the final approach corridor, altering glide paths and requiring continuous adjustment. Nightfall amplified these challenges. Even with functioning ILS guidance, pilots had to reconcile instrument readings with visual impressions, a task complicated by the weather's visual distortion. Systems. Aircraft systems were designed to mitigate risk but not eliminate it. The DC-9's autopilot could manage lateral and vertical guidance, yet inputs from pilots remained essential for stabilization in complex approaches. Instrument landing indicators, airspeed alerts, and altitude warnings offered constant information, but these signals required interpretation, prioritization, and timely action. Any misalignment between system feedback and pilot perception could narrow the margin for safe correction. In combination, these angles form a portrait of controlled complexity. There was no single point of failure. Instead, the accident's eventual unfolding was seated in the interaction of competent humans, reliable machinery, and a challenging environment, a convergence that would test the resilience of both crew and aircraft. The meticulous preparation, the years of accumulated experience, and the precise operation of the aircraft were all in motion. The stage was set, and the final approach would soon reveal the fragility inherent in even the most disciplined system. The final approach to Melbourne Airport was a study in precision under pressure. The TAA DC-9 had descended through low cloud, its landing lights piercing the rain-smeared darkness. Instruments confirmed alignment, airspeed, and glide path, but the environment was unforgiving. As the aircraft neared the runway threshold, minor deviations began to accumulate. A subtle airspeed fluctuation, barely perceptible, coincided with a slight misalignment in the glide slope. The autopilot compensated for lateral drift, but vertical corrections lagged the real-time changes imposed by shifting wind currents. For pilots, these were manageable anomalies. If detected promptly, the cockpit maintained professional calm. The captain monitored instruments, confirming altitudes and airspeed against approach charts. The first officer cross-checked readings, noting small discrepancies. In high stress, low visibility approaches, even these minor gaps can cascade. A single misjudged adjustment, altitude or descent rate, can accelerate the margin for error faster than human reflexes can correct. As the aircraft approached the runway, the combination of low visibility, wet surface, and marginal deviations led to loss of optimal touchdown alignment. The DC-9 systems function within design parameters. No mechanical failure triggered alarms. Instead, the incident arose from converging factors: environmental, procedural, and human. The aircraft made contact with the runway at an angle and speed slightly outside recommended parameters. Emergency systems activated instantly. Anti-skid braking engaged on the wet runway. Pilots applied reverse thrust and full braking, but the reduced friction limited deceleration. The aircraft skidded along the tarmac, its trajectory corrected as much as possible by the crew's rapid response. Within moments, the landing sequence concluded, leaving the aircraft in a stable, if damaged, position. There were no catastrophic explosions, no airborne breakup, only the tangible reminder that aviation is a discipline of margins. In these critical seconds, the difference between a routine landing and a serious incident is measured in degrees, seconds, and meters. The narrative of this accident is not one of spectacle, but of precision under duress and the thin margin separating control from consequence. The DC-9 had been brought down by a chain of small, cumulative factors, each minor alone, together capable of overwhelming even experienced crews. Once the aircraft had come to a complete stop, the immediate focus shifted from the flight deck to emergency response. Fire crews, ambulances, and airport security deployed according to standard procedures. Personnel moved quickly across the rain-slicked tarmac, ensuring the safety of passengers and crew. No lives were lost, but several occupants required medical evaluation for minor injuries. The calm professionalism of the response highlighted the rigor of Melbourne Airport's emergency protocols. The Australian Transport Safety Bureau, ATSB, initiated a thorough investigation. Their task was methodical: examine flight data recorders, cockpit voice recordings, air traffic communications, meteorological data, and physical evidence from the aircraft. Each piece of information was scrutinized for insight into the sequence of events that had led to the runway excursion. Flight data revealed that the DC-9's autopilot had functioned correctly throughout the approach. Lateral control remained stable, and the engines responded to throttle inputs without deviation. Altitude and airspeed variations were minor, but notable when correlated with environmental factors. Investigators emphasized that the aircraft itself performed within design specifications. Mechanical failure was effectively ruled out. Cockpit voice recordings illustrated disciplined, professional communication between the captain and first officer. Observers noted that procedures were followed, with standard cross-checks and call-outs. The recordings also highlighted the subtle human factors at play: momentary attention shifts, the challenge of interpreting instrument readings in low visibility, and the cognitive load imposed by a complex approach under adverse weather. Meteorological data confirmed persistent rain, low cloud ceilings, and variable winds on the approach corridor. These conditions reduced visual cues, altered the glide path subtly, and limited the crew's ability to rely solely on outside references. The investigation concluded that the accident resulted from a combination of environmental and human factors interacting with the operational demands of a challenging approach, a textbook example of a controlled flight into terrain scenario mitigated by professional crew response. The incident had immediate operational and procedural implications. TAA, together with the ATSB and Melbourne Airport authorities, reviewed approach protocols, enhanced pilot training on adverse weather landings, and emphasized vigilance in cross-checking automated systems against environmental observations. While the event did not result in fatalities, it reinforced a fragile margin between routine operations and critical incidents in aviation. The impact extended beyond the airline. Media coverage remained factual and restrained, focusing on the efficiency of emergency response and the professionalism of the crew rather than dramatizing the event. Regulatory authorities leveraged the findings to update standard operating procedures across domestic carriers, embedding lessons learned into training programs and procedural manuals. This incident, though minor in physical consequence, became a pivotal case study in error chains, environmental challenges, and procedural adherence, demonstrating that safety in aviation relies on the continuous integration of human judgment, machine reliability, and environmental awareness. In the months following the TAA DC-9 runway excursion, aviation authorities, airlines, and pilots revisited every detail of the event. The incident underscored a foundational truth of aviation. Even experienced crews and reliable aircraft operate within narrow margins, where environmental factors and human decisions intersect to define outcomes. Safety investigations emphasize a chain of small errors and environmental challenges, rather than assigning blame to a single cause. Procedures were refined to improve situational awareness in low-visibility approaches. Pilots received enhanced training in cross-checking automated systems against live instrument readings, and airlines instituted more frequent simulations of wet weather approaches and marginal glide path corrections. At Melbourne Airport, infrastructure and operational practices were reviewed. Runway lighting, approach signage, and instrument calibration was scrutinized to reduce ambiguity in difficult conditions. Air traffic controllers received updated briefings on monitoring aircraft alignment in adverse weather, reinforcing collaborative vigilance between tower and cockpit. The DC-9 incident became a case study in aviation safety courses, illustrating how precision, discipline, and procedural rigor mitigate risk. It highlighted the importance of layered defenses, robust aircraft systems, trained personnel, and responsive operational environments. Each layer, when functioning in concert, preserves safety even when minor deviations occur. In the quiet aftermath, lessons were embedded in everyday operations. Pilots continued to fly Melbourne approaches with an acute awareness of the interplay between machine, human, and environment. Emergency response teams honed procedures for rapid intervention. Regulators codified improvements in approach protocols. And while the event passed without catastrophic loss, its legacy endured in the strengthened culture of caution, communication, and attentiveness that defines modern aviation. Ultimately, the story of the 1996 TAA DC-9 runway excursion is not a tale of tragedy, but a reminder of aviation's relentless pursuit of safety. The incident closed not with spectacle, but with reflection, quiet, deliberate, and constructive, ensuring that every subsequent flight benefited from the knowledge gained.